In the first unit of thermodynamics, we have discussed first law of thermodynamics, thermochemistry and calorimetry. As there are some limitations of first law of thermodynamics, hence there is a need for second law and third law of thermodynamics. Hence, in second unit of thermodynamics, we will study second law of thermodynamics and third law of thermodynamics broadly. In this episode, we are going to discuss limitations of the first law of thermodynamics and need for the second law of thermodynamics, spontaneous or irreversible processes, criteria of spontaneity, entropy, statement of the second law and cyclic processes. At first, we are going to discuss the limitations of first law of thermodynamics and need for the second law of thermodynamics. First law of thermodynamics relates the heat absorbed by the system and work done by the system, but it does not tell anything about the direction of heat flow. For example, according to first law of thermodynamics, it is not impossible to extract the heat by cooling the ice to lower temperature and using that heat to warm some other liquid or water. But by experience, we know that it is not possible to transfer the heat from lower temperature to the higher temperature. On the other hand, it is also known that heat flows spontaneously from higher temperature to the lower temperature. Secondly, according to the first law of thermodynamics, the energy of an isolated system remains constant. But first law does not tell anything whether the specified process, including the chemical reaction, will take place spontaneously or whether the change is feasible or not. For example, first law does not deny the possibility of a metal bar having the uniform temperature becoming warmer at one end and cooler at the other. But by experience, we know that this process is not possible. First law also states that the energy of one form can be completely converted to the energy of another form. But heat is a special form of energy which cannot be converted into equivalent amount of work. First law does not tell anything about this concept. There is thus need of a second law of thermodynamics, that is, a law which will tell about the spontaneous processes, the direction of heat flow, and which will tell the criteria of spontaneity. The second law also helps us to calculate the maximum fraction of heat that can be converted into work in a given process. Now let's discuss the spontaneous or irreversible processes. For example, if in the expansion of an ideal gas, the external pressure is infinitesimally smaller than the internal pressure of the gas, then the expansion of the gas will take place reversibly and the work done will be maximum. But if the external pressure is much smaller than the internal pressure of the gas, then the expansion will take place irreversibly and work done will be smaller than the work done in reversible process. If the expansion takes place in vacuum, then there is no external pressure, hence the work done will be equal to 0. There are some examples for spontaneous or irreversible processes. Cliff jumping is a spontaneous process, whereas mountain climbing requires work. When a vessel containing a gas is connected to another evacuated vessel, the gas spreads throughout spontaneously unless the pressure is the same in both the vessels. The reverse process of compressing the gas into the original vessel cannot occur unless work is done on it. If there are two blocks of metal, one is hot and the other is cold, are connected, heat flows spontaneously from hot block to the cold one, never from the cold to hot. It requires work to transfer heat from one place to the other, say by means of refrigerator pump. The diffusion of a solute particles from a more concentrated solution to a less concentrated solution, when these are brought into contact, proceeds spontaneously till the concentration becomes uniformly the same, that is, till the equilibrium is attained. This process also cannot be reversed because once the concentration becomes equal, it is not possible to make solute and solvent separate without any help of external agency. Electricity flows spontaneously from a higher potential to a lower potential. The opposite direction flow of electricity is not possible spontaneously or reversibly without doing any work on it. There is an example of spontaneous chemical reaction. If solid zinc is placed in contact with aqueous solution of copper sulfate, copper is deposited or precipitated and zinc goes in solution as zinc sulfate. Some heat is also evolved in this spontaneous reaction. If we try to reverse the direction of the reaction, then some electric current has to be passed in the solution of zinc sulfate in which zinc rod and copper rod are dipped. Electricity used for this process will be more than the heat produced in the direct reaction. Molecules spontaneously migrate or diffuse from regions where their concentration is high into the regions where their concentration is low. The reverse process does not occur spontaneously because work is required to separate the molecules once they have mixed. It may be concluded that the physical or chemical changes which are naturally occurring, that is, which take place spontaneously of their own, are all irreversible in nature. Work can be obtained from a spontaneous process, but as this process is irreversible, hence work obtained in a spontaneous process is less than the work obtained in a reversible process. Now we are discussing some important criteria for spontaneity of the reactions or physical changes. A spontaneous change is one way or unidirectional. For reverse change to occur, work has to be done. For a spontaneous change to occur, time is no factor. A spontaneous reaction may take place rapidly or very slowly. If the system is not in equilibrium state, that is, it is unstable, a spontaneous change will continue till the system attains the state of equilibrium. And once the system is in equilibrium state, it does not undergo any further spontaneous change in state if left undisturbed. To take the system away from the equilibrium, some external work must be done on the system. Generally, a spontaneous change is accompanied by decrease in internal energy or enthalpy. Hence, it implies that only such reactions are spontaneous which are exothermic reactions. But melting of ice and evaporation of water are endothermic reactions, and yet they are spontaneous. Hence, there must be some other criteria other than delta H which will govern the spontaneity of a physical or chemical change. This criteria is given by the second law of thermodynamics, which is known as entropy. Careful examination shows that in each of the processes, that is, melting of ice or evaporation of water, there is increase in disorderness or randomness. The water molecules in ice are arranged in a highly organized crystal pattern which permits little movement. As a sample changes from solid to liquid to gas, its particles become increasingly more disordered, hence greater dispersal of energy will take place, so its entropy will increase. As the ice melts, the water molecules become disorganized and can move more freely. The movement of molecules becomes freer when the water evaporates into space, as now they can roam about throughout the entire atmosphere. In other words, it can be said that the randomness or disorderness increases when ice melts to water and water evaporates to water vapor. A change that brings about more randomness is more likely to occur than a change which brings about more order. Let us suppose we have a suite of playing cards arranged numerically. Here we can see that the sequence of cards is certainly highly organized. Now, if we throw the cards into the air, collect them and restack them, we will almost surely find that they have been placed at random. This is expected because when the cards are tossed, there are many ways for them to be disordered, while there is only one way for them to come together again in their original sequence. Thus, on the basis of law of pure chance, the disordered sequence is more probable than the ordered sequence. This law of probability is also applicable on physical and chemical changes. Now let us define entropy. Entropy is a thermodynamic state quantity that is a measure of the randomness or disorderness of the molecules of the system. The symbol of entropy is capital S. The change in entropy from initial state to the final state is represented by delta S. This is the change in disorderness or randomness. The entropy of a system is a state function. That is, it depends only on the state of the system and it does not depend on the path by which that state has been achieved. Change in entropy is given as entropy of final state minus entropy of initial state of the system. If entropy of the system increases, then delta S will be positive. A process accompanied by the increase in entropy will be the spontaneous process. Let us consider a molecular system in states A and B. In state A, all the molecules are arranged and highly ordered, while in state B, the molecules are present at random and it is highly disordered. Now, by definition, the entropy of A is lower and that of B is higher. According to the law of chance or the law of probability, the B state is more probable than A state. Hence, the change of A from B will be spontaneous change. The second law of thermodynamics states that whenever a spontaneous process takes place, it is accompanied by an increase in the total entropy of the universe. More specifically, we take universe equal to surroundings plus system. Therefore, change in entropy of universe will be equal to delta S system plus delta S surroundings. The second law tells us that when an irreversible spontaneous process occurs, entropy of the system and that of surroundings increases. Therefore, delta S universe is greater than 0. But for a reversible change, delta S universe will be equal to 0. Since the entire universe is undergoing a spontaneous change, hence second law of thermodynamics can be concisely interpreted as the entropy of the system is constantly increasing. Change of ice to liquid and then to water vapor is accompanied by increase of entropy with increasing disorder. The table given provides an example of the difference between the entropy of a substance in the solid, liquid and gaseous phase. The entropy of solid, liquid and gaseous forms of sulfur trioxide are given as standard entropy for solid sulfur trioxide is equal to 70.7 joule per Kelvin per mole. Standard entropy for liquid sulfur trioxide is equal to 113.8 joule per Kelvin per mole. And standard entropy for gaseous sulfur trioxide is equal to 256.76 joule per Kelvin per mole. Note that the units of entropy are joule per mole per Kelvin. The graph of entropy versus temperature for solid, liquid and gaseous sulfur trioxide is given here. In this graph, you can see that entropy of the solid sulfur trioxide increases as it is converted to liquid sulfur trioxide and the entropy of liquid sulfur dioxide also increases as it converts to gaseous sulfur trioxide. Up to now, we have discussed the physical definition of entropy, but classical thermodynamics need an operational definition of entropy so that entropy change of universe, that is, entropy change of system and entropy change of surroundings, can be calculated. In 1850, Clausius calculated entropy and given numerical definition of entropy. According to Clausius, if Q amount of heat is absorbed by the system, then the change in entropy or increase in entropy of the system is given by Q upon T. And if the same amount of heat is liberated by the system, then Q upon T is the decrease in entropy of the system. Thus, entropy can precisely be defined as: for a reversible change taking place at a fixed temperature T, the change in entropy delta S is equal to heat energy absorbed or evolved divided by the temperature T. That is, delta S is equal to Q upon T. If heat is absorbed, then delta S will be positive and there will be increase in entropy of the system, and if heat is evolved, then delta S will be negative and there will be decrease in the entropy of the system. As entropy is the heat energy absorbed or evolved divided by the absolute temperature, hence units of entropy are units of heat divided by the units of temperature. Therefore, the unit of entropy will be calories per Kelvin, or SI unit of entropy will be equal to joule per Kelvin. Let us define standard entropy. The absolute entropy at 25 degrees Celsius, that is 298 Kelvin, and 1 atmosphere pressure is called standard entropy. Standard entropy is represented by the symbol S0. All perfect crystals at 0 Kelvin has standard entropy value equal to 0. But above the 0 Kelvin, all the substances has positive standard entropy value. You can see the standard entropy values of various substances in this table. For solid silver, entropy is 41.32 calories per mole per Kelvin or 172.9 joules per mole per Kelvin. For gaseous hydrogen, it is 31.21 calories per mole per Kelvin or 130.6 joules per mole per Kelvin. For gaseous carbon dioxide, entropy is equal to 51.06 calories per mole per Kelvin or 213.6 joules per mole per Kelvin. For solid potassium, entropy is equal to 38.30 calories per mole per Kelvin or 160.2 joules per mole per Kelvin. In this table, you can see the entropy of various other substances also. If we know the standard entropies of various substances, we can calculate the standard entropy change of a chemical reaction by using the expression delta S of reaction equal to summation of S0 values of products minus summation of S0 values of reactants. Now we will define the standard entropy of formation. Standard entropy of formation is the entropy of 1 mole of the substance when it is formed from its constituent elements in their standard state. Standard entropy of formation is denoted by the symbol S0F. We can calculate the standard entropy of formation of a compound by the values given of standard entropy of the elements. We can use the relationship standard entropy of formation of the compound will be equal to standard entropy of the compound minus summation of standard entropies of the elements. Here is an example to understand the calculation of standard entropy of formation of a compound. Calculate the standard entropy of formation delta S0F of gaseous carbon dioxide given that standard entropies of gaseous carbon dioxide, solid carbon and gaseous oxygen are 213.6, 5.740 and 205.0 joule per mole per Kelvin respectively. We know that S0F is equal to S0 compound minus summation of S0 elements. Therefore, S0F of carbon dioxide will be equal to S0 of carbon dioxide gaseous minus S0 of solid carbon plus S0 of gaseous oxygen. Now substituting these values in the equation, we will get S0F equal to 213.6 minus 5.740 plus 205.0 joules per mole per Kelvin, which is equal to 213.6 minus 210.74 joule per mole per Kelvin, which is again come out to be 2.86 joules per mole per Kelvin. Hence, standard entropy of formation of gaseous carbon dioxide will be equal to 2.86 joule per mole per Kelvin. Before going to heat engines, let us discuss cyclic process. When a system, after completing a number of processes, comes back to its original state, the system is said to have completed one cycle, and the process is known as cyclic process. As internal energy is a state function, that is, it depends on the state of the system and not on the path by which that state has been attained. Hence, internal energy change for a cyclic process remains 0. Therefore, delta U equal to 0 for a cyclic process. From first law of thermodynamics, we know that delta U is equal to Q plus W, as delta U is equal to 0. Hence, for a cyclic process, Q is equal to minus W, or we can say that W is equal to minus Q. If the series of changes in a cyclic process are conducted at constant temperature, then it is said that it is isothermal cyclic process. If the series are conducted reversibly, then it is said a reversible cycle. Now let us revise what we have discussed today. First, we have discussed the limitations of first law of thermodynamics. First law of thermodynamics does not tell us anything about the direction of heat flow and spontaneity of a chemical or physical change. Then we discussed the spontaneous or irreversible processes. All naturally occurring irreversible processes are spontaneous. Under criteria of spontaneity, we discussed a new term known as entropy. Entropy is the measure of disorderness or randomness. Mathematically, we can say that delta S, that is change in entropy, is equal to Q upon T, where Q is the heat change during the process. The second law of thermodynamics in general way can be defined as, in a spontaneous process, there is increase in entropy. And in last, we discussed a cyclic process. In continuation, in next episode, we will discuss heat engines and Carnot cycle.